Hello. In this video, I would like to help you practice translating trigonometric graphs and identifying phase shifts. In order to see how trigonometric functions like sine, cosine, and tangent fit real-world data, they must be modified from their most simple form. Often you will see four different coefficients introduced within any trigonometric function. And these four coefficients account for the two most common transformations, shifts and stretches. The coefficient A affects vertical stretches. Large values of A will stretch the graph taller, but smaller values, close to zero, will compress the graph shorter. The coefficient B affects horizontal stretches, but it behaves in the opposite manner. Large values of B will compress the graph, whereas small values, close to zero, will stretch the graph wider. These transformations will not be covered in this video, but are worth noting now so that you are aware of them when you encounter them in the future. The coefficient C affects horizontal shifts, and like the B value, it behaves in the opposite manner than what you might expect. Adding a C value will shift the graph to the left, whereas subtracting a C value will shift the graph to the right. Finally, the coefficient D will affect vertical shifts, and it will make the graph behave as you might expect. Adding a D value will shift the graph up, and subtracting a D value will shift the graph down. Perhaps you have also noticed that both coefficients that are added within the function account for shifting, whereas both coefficients that multiply within the function account for the stretching of the function. If we consider graphing the functions below, it might be easier to consider where the origin of the graph translates, then draw our function off of it. I believe a scale of 30 degrees per grid line horizontally will work well for these examples. With a C value of -60 and a D value of -1, I know the graph is shifted to the right 60 degrees and down 1 unit. We can lightly sketch a new origin and a set of axes here. Now, by considering the key data points for the cosine function, we can plot points and establish the graph. On the new axes, there is a coordinate at 0, 1. Another point is found on the new axes at 90 degrees, 0. Then we can plot 180, -1, and 270, 0. We ran out of room in this direction, but can continue the pattern on the left side of the graph. The graph of the tangent can be completed in much the same way. The new axes are moved to the left 45 degrees and up 2 units. From this location, we can establish key data points and asymptotes, then generate the rest of the graph of the function. To better understand the true representation of these graphs, it would be a good idea to erase your temporary axes. In the last two examples, I would like to establish the trigonometric functions. In the example on the left, we have a wave function that could be either sine or cosine. To find the sine function that fits this graph, we could say that the new origin and axes are located here, which are 45 degrees to the right and 1 unit down from the initial origin. This means that our C value is negative 45 and our D value is negative 1. The function that fits this graph, therefore, is as follows. Can you determine the cosine function that fits this curve? Please try establishing it on your own. Pause the video now and resume playback in a moment to check your work. The cosine function is similar to the sine function, but has a horizontal shift that is 90 degrees further to the right. In fact, the only difference between a sine and a cosine function that represents the same graph is only a shift of 90 degrees. Our last example appears to be a tangent function with a horizontal shift of 60 degrees and a vertical shift of 1 unit. So the function here would be an appropriate fit for the data. For more practice, I suggest that you create trigonometric functions like these and sketch them on your own. Then use a graphing utility to check your work. Good luck.